Hello everyone, and welcome to the online lecture for college algebra. In this video, we're going to cover section P2 on properties of exponents, and in this section, we're going to be specifically using what are called integral exponents, in other words, integers as exponents. Having said that, the properties that we cover in this section actually work for all exponents, and you will see them come back again very soon in section P3. So before we get started, let's make sure we're all on the same page. When we talk about integers, we know what we mean. And so the set of integers in mathematics is the set of numbers that are 0, 1, 2, so on and so forth, 3, 4, 5, 6, 7, but also negative as well. -1, -2, forever to the left. So in other words, they're often called the positive and negative whole numbers. No decimals, no fractions. So with that said, let's go ahead and get started on properties of exponents. So the first thing we're going to talk about in this section is how we handle negative exponents. And this is something a lot of students have a little bit of trouble with if they're not very comfortable with their exponent properties. So if a, which is going to be what we call the base of the exponent, it is the thing that's being raised to the power, is a non-zero real number, and n, the exponent, is a positive integer, again because we're dealing with integer exponents in this section, but really n could be any real number. Then if you've got a to the negative nth power, that's actually equivalent to 1 over a to the positive nth power. So for example, if you had 2 to the negative second power, that would be the same as 1 over 2 to the positive second power, or 1 over 4. It also works in reverse. So if you have a negative exponent in the denominator of a fraction, right, just imagine multiplying both of these exponents by -1, and they just flip places. So in other words, you can bring it up to essentially the numerator of an exponent. That's what we're doing here. We're taking reciprocals when all is said and done, and write the exponent as a positive. And we'll get back to that reciprocal idea in just a minute, where we look at the more general forms of this idea. So in example 1, we're asked to simplify some expressions involving negative exponents. And this is a term you're going to see a lot in chapter P, especially expressions. That just basically means that we're not dealing with an equation. There is no equal sign. We're not going to be moving things across. We're not going to be trying to solve for variables or anything like that. We're just going to take what's there already, and we're going to try to manipulate it to simplify it as much as possible. So with that said, try pausing the video now and use the properties of negative exponents that we talked about on the previous slide to simplify these expressions. All right, so let's take it one at a time. In part A, we've got 3 to the negative first power, which would just be 1 over 3 to the first power, times 5 to the negative second power, which would be 1 over 5 to the positive second. And this is times 10 squared. That's not a negative exponent, so we don't have to flip it. So this is 1/3 times 1/25 times 100, and you could write that as over 1 if you want to think of it as a fraction. And then to multiply fractions together, you just multiply the numerators together, and you multiply the denominators together. So we're going to have 1 times 1 times 100 in the top, and 3 times 25 times 1, which would be 75, in the bottom. Now both 100 and 75 are multiples of 25, so we can reduce this fraction. If we divide both the top and bottom by 25, that would reduce us to 4/3. For part B, we've got 2/3 to the negative third power. So if we apply the definition on the previous slide, this would be the same as 1 over 2/3 to the positive third power. Anything cubed is just multiplied by itself 3 times essentially. So we've got 2/3 times 2/3 times 2/3. And so again, just like before, to multiply fractions, multiply numerators and denominators. 2 times 2 times 2 would be 8. 3 times 3 times 3 would be 9 times 3, or 27. But dividing by a fraction is the same as multiplying by its reciprocal. So 1 divided by 8 over 27 would be the same as 1 times 27 over 8, or in other words, just 27/8. Then last but not least, we've got part C. We've got 6 to the negative second power divided by 2 to the negative third power. So I'm going to apply the definition to both the top and the bottom of this fraction. So in the top, we've got 6 to the negative second power, which would be 1 over 6 squared. 2 to the negative third would be 1 over 2 to the 8th, or excuse me, 1 over 2 to the third power, getting a little ahead of myself there. And so that would be 1 over 36 divided by 1 over 8. But once again, divided by a fraction is the same as multiplying by its reciprocal. So instead of dividing by 1 over 8, we can multiply by 8 over 1. And so these are easy fractions to multiply. 8 times 1 is 8. 36 times 1 is 36. Now both 8 and 36 are multiples of 4, so we can reduce this fraction by dividing both the top and the bottom by 4, and that would give us a fraction of 2 over 9. So let's expand that idea of negative exponents, and let's take a closer look at how they interact with fractions, because we were dealing with that in both parts B and C of example 1. And there are two properties related to this. The first is that if you have a fraction raised to a negative exponent, you can actually just take the reciprocal of the fraction itself to make the exponent positive. So you don't have to think of it as 1 over a over b to the nth power. You can instead just flip the fraction on the inside and raise it to the positive nth power, which will save you a step or two in simplification. The other property is that if you have a fraction with a negative exponent on both top and bottom, then basically both just flip spaces. This is just a combination of both of the properties on the first slide. The a to the negative m comes down to the denominator as a to the positive m, and the b to the negative n in the denominator comes up to the numerator as b to the positive n. So you don't have to break that down into two different fractions, 1 over a to the m divided by 1 over b to the n. And in fact, you can even see this by simplifying this. Dividing by the fraction is the same as multiplying by the reciprocal, and you can see that you get the same result. And so now let's revisit parts 1b and c with these new properties and see how it makes our problems a little bit faster. So in 1b, we had 2/3 to the negative third power. So by this new property up top, that would be the same as the reciprocal 3/2 to the positive third power. So 3/2 times 3/2 times 3/2, which would give us 27 over 8. And we can even speed up that property, or that process, when we get to another property a little bit later on in the section. Similarly, for part 1c, the 6 to the negative second would just come down to the bottom of the fraction as 6 squared, and the 2 to the negative third in the bottom would come up to the top as 2 cubed. And so this would just give us 8 over 36, which would once again just reduce to 2/9. So now let's build up some remaining rules of exponents in this section. I'm going to show you some examples to explain where these properties of exponents are coming from. So we're going to start with something called the product rule. So to start off here, I want you guys to consider the specific case of a squared times a cubed. And let's think about what that means. So we can break both of these down into parts. A squared, you could write as a times a. And this is times a cubed, but a cubed is just a times a times a. And so what you end up with in this case is 5a's multiplied together. So this is just actually equal to a to the fifth. This leads to something called the product rule, where you just add the number of a's in each term together. You had 2a's for the a squared, you had 3a's for the a cubed, which gave you a total of 5a's in this case. So a squared times a cubed would be a to the 2 plus 3, or a to the fifth. So this leads us to something called the product rule, where in general, a to the nth times a to the nth is equal to a to the m plus n power. Now it is important to note that this only works if they're the same base. You can only combine these together if they're all a's in this case. So if you had something like 2 cubed times 3 to the fourth, these you couldn't combine because the bases are different. 2's and 3's won't combine together to give you a same base with a bigger exponent. The quotient rule works similarly. So to illustrate this, I want you to consider a squared divided by a cubed. Well, once again, we can break these down into pieces. A squared we can write as a times itself. A cubed would be 3a's multiplied together, and then this fraction reduces, it divides. And so this cancels out and just leaves us with 1 over a, right? Because the process of canceling fractions is dividing, that doesn't leave you with a 0 on top. It leaves you with a 1. A divided by a is 1. Or in other words, to combine this with our idea of negative exponents from earlier, this would be a to the negative first power. And so because these a's in the denominator are taking away from the a's in the numerator, this time around you subtract the exponents. A squared divided by a cubed is equal to a to the 2 minus 3, or a to the negative 1. So in other words, in the general case, a to the m divided by a to the n is equal to a to the m minus n. This is the quotient rule of exponents. And again, it only works if you've got the same base a. Three more to go with similar ideas. So for the power of a power rule, imagine if you had a cubed squared. Well, by definition, that would be a cubed times itself. So a cubed times a cubed, which using the product rule on the previous slide would give us a to the 6th power. And so notice how that's related. 3 plus 3 you can also think of as 2 times 3. If we adjusted this a little bit and wrote it as a cubed cubed, so in other words, it was a cubed times itself 2 more times, that property of products you could apply piecewise, and it would extend. It would just give you a to the 3 plus 3 plus 3, or 3 times 3. So in other words, you're essentially just multiplying the exponents together. A cubed squared would be a to the 3 times 2 power, or a to the 6th. And in general, a to the mth in parentheses, the parentheses are important here, raised again to the nth power is just a to the m times nth power. For the power of a product rule, consider the case a times b cubed. So we've got two different bases now, a and b. Well, again, by definition, anything cubed, we're going to multiply itself in 2 more times. So ab times ab times ab. So let's just think about this. This is a times b times a times b. And again, times a times b. But multiplication with real numbers is commutative, meaning the order doesn't matter. 2 times 3 is the same as 3 times 2. they both give you 6. So we can rearrange these terms. I'm going to choose to rearrange this so that my a's are together, a times a times a, and my b's are together, b times b times b. So this is actually just a cubed times b cubed. And notice what happened here. The exponent essentially distributes to each term in the product. And so in the general case, if you've got a, b to the mth power, that's just equal to a to the mth power times b to the mth power. Exponents distribute across multiplication, which is really useful. A similar idea will hold for fractions as well. So a divided by b cubed, don't even have to do rearranging this time, would be a divided by b times itself 2 more times. To multiply a fraction, you multiply the numerators, multiply the denominators, and so again, the exponent essentially just distributes to both the numerator and denominator. And in the general case, a over b to the mth power is a to the mth power over b to the mth power. So let's summarize these rules of exponents. So this is 5 new properties in total. If you multiply 2 with like bases, you just add their exponents together. If you divide 2 exponential expressions with like bases, you subtract their exponents. If you have a power in parentheses raised to another power, you just multiply the exponents together. And then properties 4 and 5 are really nice. Exponents essentially just distribute across multiplication and division. No problem. It's actually addition and subtraction where things get really messy, right? Unfortunately, it doesn't work quite as well with those. You'll notice that's missing. So a plus b squared is not the same thing as a squared plus b squared. It does not distribute. And in fact, if you have something that looks like this, we have the process of foiling to tell us how to handle that, which we'll talk about later on in the course. And the only reason foiling exists is because exponents cannot distribute across addition or subtraction. For our last property, this one is a lot more specific. Let's talk about zero exponents. And so we say if our base a is some non-zero real number, then no matter what a is, anything raised to the 0th power will always be equal to 1. Now I'm not going to show you guys the proof of this because proofs get really complicated in math, but I can give you a justification. So for a second, consider the situation where we've got 2 to the negative third times 2 to the positive third. By the properties of exponents that we saw on the previous slide, we're multiplying 2 exponential expressions together with like bases, so that simplifies by adding their exponents together. In other words, this is a really complicated way to write 2 to the 0th power, because that's what I'm interested in getting at here. But let's simplify this instead by just writing 2 to the negative third as 1 over 2 to the third. And this will still be times 2 to the positive third, but that's 1 over 8 times 8, or 8 divided by 8, which would just give you 1. So in other words, 2 to the 0th power is in fact actually equal to 1. And the same process would have worked no matter what we had chosen for our base 2, which is why it works for any base a. All right, so we've covered all the properties of exponents. From here on out, it's just examples. So in example 2, we're asked to simplify some expressions involving exponents. We're just going to use the properties of exponents. So try pausing the video here and see if you can find the answers to parts A and B of example 2. All right, so part A initially looks complicated if you're not comfortable with algebra, but ultimately it ends up just being multiply-like terms when all is said and done, because there's no addition or subtraction getting in the way. And so let's just think about this. That first term is 3 times x to the 8th times y squared. This is times the second term, which is negative 2, times x times y to the 4th. But again, I'm going to go back to that same operation that I talked about a little bit earlier, where multiplication is commutative. The order doesn't matter, so we can rearrange these things. And that's why we can combine like terms together. It's because multiplication is commutative. So I can rewrite this as 3 times negative 2 times x to the 8th times x times y squared times y to the 4th. And now we can just multiply like terms together. So 3 times negative 2 would give us negative 6. X to the 8th times x, by properties of exponents, would be 8 to the x plus 1, or x to the 9th. And y squared times y to the 4th would be y to the 2 plus 4, or y to the 6th. Part B is actually a little bit like a trick question, because if you try to approach this using properties of exponents, none of them apply. Because the bases aren't the same here, you've got a base of 2 and a base of 3, you can't use the same property of exponents that we were doing in part A. So in other words, this is not even really a property of exponents problem. Nothing applies. So you can just write this as 2 cubed, which is 8, times 3 squared, which is 9, and 8 times 9 is, of course, 72. So once again, try pausing the video and see if you can find the solutions to part C and D of example 2. All right, so for part C, I'm not going to bother to write out the rearranging this time. I'm just going to jump straight into multiplying the like terms. For the numbers, we're going to have 3 times negative 4, which is a negative 12. For the x's, we've got x to the second times x to the negative second. So we're going to add the exponents together. And for the y's, we've got y cubed times y to the negative 5th. So again, we're going to add the exponents together. So for the x's, we've got a positive 2 and a negative 2, which is x to the 0 when we combine it together. But remember, anything raised to the 0th power is 1. So this is actually just negative 12 times 1. Then for our y's, we've got 3 plus a negative 5, 3 minus 5, which would give us y to the negative second. Well, the 1 we can just drop because multiplying by 1 doesn't change anything. My last step here is that a lot of times we don't like leaving negative exponents in our final answer. Negative 12 times y to the negative second is correct, but it looks a little bit nicer if we bring that negative second power down to the denominator. Remember, y to the negative second is 1 over y squared. And then we multiply that by negative 12. In fact, let me write out the details for this one, which would just give us negative 12 over y squared. D seems pretty complicated at first, but it's actually a relatively simple problem as well, because just like we were multiplying like terms, you can divide like terms here as well, because again, there's no addition or subtraction taking place. As long as all you have is multiplication and division, things tend to combine really nicely together. It's the interactions between multiplication and division and addition and subtraction where the rules start to get a lot more complicated. So let's just divide like terms. So for the numbers, we've got negative 6 divided by 2, which would just divide to give us a negative 3. For the a's, we've got a to the 5th divided by a to the 7th. This is division this time. So we're going to subtract exponents. In other words, that would just leave us with 2 a's left over in the denominator, but I'll touch on that more in just a second. And then for b to the negative 1 divided by b to the negative 3, same idea. The exponent in the top, negative 1, and then we'll subtract from that the exponent in the bottom, negative 3. And so that leaves us with a to the negative second. And then for b, that turns into negative 1 plus 3, or b squared. And once again, I can bring that a down to the bottom of a fraction and write this as negative 3b squared over a squared. Now, I'm going to show you an alternate way to visualize these problems. For part C, 3x squared y cubed, there are no negative exponents there, so we can leave it like it is. But for the negative exponents in the second one, let's bring those down to the bottom of a fraction. So let's think of that as negative 4 divided by x to the positive second, y to the fifth. Then if we multiply these two fractions together, this would give us negative 12 x squared y cubed divided by x squared y to the fifth. And so if you think of it like this, the x's divide each other away, the x squareds cancel, and then if you've got y cubed divided by y to the fifth, essentially the y cubed in the top will cancel out 3 of the y's in the bottom, leaving you with negative 12 over y squared. So pretty often in algebra, we'll do fraction reduction by thinking of it this way, but really what's still happening at the end of the day is that these properties of exponents are taking place just kind of behind the scenes when you think of it as fraction reduction. Similarly, for part D, if I think of the numerator as negative 6 a to the fifth divided by b, bring the b to the negative first down to the denominator, divide this by the bottom, which is 2a to the seventh divided by b cubed, dividing by a fraction is the same as multiplying by its reciprocal. And then what will happen in this case is that the b in the bottom will divide away one of the b's on top. The 5 a's on top will cancel out 5 of the a's on bottom. And then the 2 will divide into the negative 6. And so what you would be left with is negative 3b squared divided by a squared. So you can also think of that one as fraction reduction. So for our final problem, our final example, let's start to make things a little bit more complicated. So once again, try pausing the video and see if you can find the solutions to example 3. All right, so for part A, we're going to start by applying the power of a power property. Or excuse me, rather the power of a product property. Now the one we looked at before was only for a product of two terms. A times b to the mth was a to the mth power times b to the mth power. But this actually extends for a product of any length. Because let's think about this. If you've got three things multiplied together, a times b times c raised to the mth power, you can think of this as a product of two things. Break it up into parts. Let's say we think of this as ab times c to the mth power. So if we apply the power of a product rule once, this would be a times b to the mth power times c to the mth power, but then you would just apply the property a second time. A to the mth power, b to the mth power, c to the mth power. So no matter how many things you have multiplied together, the exponent just distributes across all cases. So what that means for part A is that this is going to be negative 3 to the fourth power times x to the a minus fifth to the fourth power times y to the negative third to the fourth power. Just raise each of the three terms to the fourth power. So let's start with negative 3 to the fourth. That would be negative 3 times itself, 4 times in total. And so I'm going to evaluate this by a calculator, without a calculator, by breaking it up into pieces. each pair of negative 3's would turn into a 9. And so that would be a positive 81. And now the second term is where we need to be the most careful here. Now we're going to apply the power of a power property and multiply these exponents together. But you need to be a little bit careful whenever you have an exponent with multiple terms like this. Essentially, the entire exponents need to be multiplied together. So if you've got one in multiple terms, put it in parentheses because it's going to have to distribute. So this is going to be x. The entire exponent of a minus 5 needs to be multiplied by that exponent of 4. That's going to have to distribute through. The second one is significantly easier because there's just one term. That's going to be y to the negative 3 times 4. And so this gives us 81 times x to the 4a minus 20 times y to the negative 12th. And the last thing we might do to simplify this is bring that y to the negative 12th down to the denominator as y to the positive 12th. You could actually break this up into two separate x's using the reverse of the quotient rule. So you could actually write that as x to the 4a divided by x to the 20th, but that actually makes the problem less simplified. We want to keep it with as few x's as possible. And so that's as good as it gets. Part B combines a bunch of our properties of exponents together. There's a lot going on in this one. The first is that we've got an exponent, or rather a fraction, raised to a negative exponent. So I'm going to start by flipping the fraction on the inside. And then changing the exponent to a positive 3. Now I'm going to apply, let me make some space up here. So now I'm going to apply the power of a quotient rule, which says that exponents essentially just distribute to the top and the bottom of a fraction. So this is going to be the top 2a to the negative 3m cubed divided by the bottom 3a to the 2m minus 1 cubed. Now both the numerator and denominator of this fraction is a product. 2 times a to the negative 3m. 3 times a to the 2m minus 1. So now I'm going to apply the power of a product rule to both the numerator and the denominator. So this is going to be 2 cubed times a to the negative 3m cubed divided by 3 cubed times a to the 2m minus 1 cubed. The numbers are easy enough. 2 cubed is 8. 3 cubed would be 3 times 3, which is 9, times 3 again. So 27. And then for the terms with a, we're now going to apply the power of a power property. So for the a to the negative 3m cubed, that's going to be negative 3m times 3. Same thing for the bottom. A to the, and again, be careful with parentheses here, 2m minus 1 times 3. So let's start by simplifying that. The numerator is easy enough. Negative 3m times 3 would just be a negative 9m. Essentially multiply like terms together again. In the denominator, we need to distribute. So that would be, if we distribute the 3 through, a to the 6m minus 3. And we're close, but we need to go one step further, because now we've got a common base of a in both the numerator and denominator, so we can combine these together using the quotient rule. Subtract the exponents. And again, be careful, because we've got an exponent with multiple pieces, I'm going to put that exponent in parentheses because I need to subtract the whole thing off. Very easy mistake to make. So this is going to be 8 over 27. And I'm going to go ahead and bring the 8 over 27 out and just separate the a from the fraction completely. And this is going to be a. The top exponent was negative 9m, but then I'm going to subtract from that the bottom exponent of 6m minus 3. That minus sign will distribute through. So that's a negative 9m minus 6m plus 3. And then because we have some like terms with m's here, the last thing we can do is combine those together. And so we've got 8 over 27 times a to the negative 15m plus 3. And because there's variables in the exponent, I don't know if that's positive or negative. I'm not going to flip that. We're just going to leave it as is. And you could even put that a back in the numerator of the fraction if you really wanted to. That's about as messy as problems in this section could possibly get. That combined together just about every one of our properties of exponents, along with some tricky situations where the exponents have multiple pieces, making sure that you're careful with your parentheses. All right, so in conclusion, there are a lot of properties of exponents that you need to make sure you're familiar with. These are foundational to a lot of the work that we do in algebra and foundational to pretty much just math in general. Properties of exponents are very important. So make sure you're familiar with them all. Make sure you know how to handle negative exponents. Again, these are basically 4 properties involving negative exponents, which all just amount to take the reciprocal and make the exponent positive. Make sure you know that anything raised to the 0th power is equal to 1. And then make sure you know how to handle these 5 rules of exponents that we talked about. The product rule, the quotient rule, the power of a power rule, power of a product rule, power of a quotient rule. And you do not have to remember the names of the rules. You just have to know how to simplify exponents. All right, so with that said, that's it for section P2. If you guys have any questions about the material, please make sure you let me know, and I will see you in the next video.